Chapter 5. An overview of filter design. In this chapter, the necessary steps in the design of a digital filter are reviewed. The objectives of this chapter are basic familiarity with the concept of filtering and FIR and IIR filters, finite impulse response for FIR, and infinite impulse response for IIR. Okay. The main terms used to describe filters in the frequency domain, say it passband, stopband, ripple, etc. Ability to identify and select FIR or IIR to meet the desired design requirements, identifying possible sources of degradation due to limited word length. Right. The next topic. Basic introduction to the concept of filtering. Here you see some frequency selective filters, low pass filter, high pass, band stop. Why it is called low pass? Look at the frequency. Okay. It just permits passing low frequencies. Okay. So it's called low pass. What about high pass? Okay. You see here, 0 is not permitted to pass, but higher frequencies, band pass and band stop. Later you'll get more familiar with the idea. Okay. Figure 5.1 shows some of frequency selective filters. The cutoff frequencies for low pass, high pass, band pass, and band stop filters are respectively equal to 0.2 times pi for low pass and 0.8 times pi for pass, and two cutoff frequencies for band pass. The first one 0.4 pi and the second 0.6 times pi. For band stop, the same story. Okay? They are related to the figure. Now, ideally, for a period from minus pi up to pi, we have H related to low pass filter is equal to 1 apps of omega, then cutoff frequency omega c. Otherwise, 0. Okay, up to the most possible frequency, highest possible frequency, which is pi. In time domain, a low pass filter will be equal to 1 over 2 pi integration from minus omega c up to omega c, 1, the domain 1 times e to the power of j omega n d omega, which will be equal to a sinc. Okay. You see here the amplitude and the response. If n is equal to 0, the result will be omega c over pi. Otherwise, it will be omega c over pi times sine of omega c times n over omega cn. Right. In real terms, due to the non-causality of the impulse response, it needs time shift. Therefore, the effect in frequency domain will be e to the power of minus j times omega times n0 multiplied by h low pass filter of e to the power of j omega. Okay? That's the result for a shift in time domain. Okay. As a result, H low pass filter of e to the power of j omega will be equal to e to the power of minus j omega nd if apps of omega is less than cutoff frequency of c, otherwise 0. And in time domain, I don't want to read it because it will take time. You see here the complete idea, okay? For a high pass filter, similarly, we'll have H related to high pass filter will be equal to 0 if absolute omega is less than or equal to cutoff frequency. Otherwise, it will have permission to pass the components, which will be equal to e to the power of minus j times omega times nd. Okay? It means that high pass filter has frequency components which is equal to 1 minus those related to low pass filter. Okay? It's very important idea. Or in time domain, related to high pass filter of n will be equal to delta n minus h low pass filter of n, which is equal to delta n minus omega c over pi times sine omega c n minus nd over omega c times n minus nd if n is not equal to n delay samples. Otherwise, if it's so, it will be 1 minus omega c over pi. Okay, now take home. Calculate H high pass filter of n directly from the inverse Fourier transform, considering the shape of high pass filter in frequency domain. Your answer should be as follows. H high pass filter of n equal to omega c over pi times sine pi times n minus nd minus sine omega c times n minus nd over omega times n minus nd if n is not equal to nd. Otherwise, it will be pi minus omega c over pi. Now, prove that the impulse response of the high-pass filter calculated from the two equations 5.3 and 5.4 are the same. Okay? In a similar way, find the frequency responses as well as the impulse responses of band-pass filter and band-stop filter and confirm correctness of the following relations. For bandpass filter, we'll have H bandpass filter of n will be equal to omega c2 over pi. C2 means the second cutoff times sine of omega c2 times n minus n delay over omega c2 times n minus n delay minus omega c1 over pi times sine of omega c1 times n minus n delay over omega c1 times n minus n delay, where n is not equal to n delay. Otherwise, it will be equal to omega c2 minus omega c1 over pi. Right. And for band stop filter, I don't want to read the details. It will take time. You may pause the video and have details. Okay? Similar idea. I'll leave it for you. The third part of take-home. Rewrite the above equations using sync. Okay? Sync means just this term over this term. It will be simplified. Now, suppose x of n is equal to cosine of 0.1n plus cosine of 0.4n is going to be filtered with a very simple high-pass FIR filter of length 3 so that its first component is removed as much as possible while keeping the second one. This example is very important. You'll get familiar with simple ideas of filtering. You are not experienced by default, but later you will be. Anyhow, you got the idea. Two terms, low frequency, high frequency. For this purpose, if you have written down the equation, we will have no permission for the first component. So h of e to the power of j times 0.1 will be 0, but the next one has permission to pass. Okay? Now, 3 length 3 means h of n is equal to alpha, beta, and gamma. Of course, gamma needs to be equal to alpha. You will find why. You will find out it here. H of e to the power of j omega is equal to alpha plus beta times z minus 1, or equivalently e to the power of minus j omega plus alpha times e to the power of minus j2 omega, or z minus 2 if you are going to use h of z. But here we are interested in frequency response. Now, very simple calculation. Okay, you see here what is happening, which will lead to e to the power of minus j omega times beta plus 2 times alpha times cosine of omega. Now you see here why we have chosen gamma to be alpha, because we can have such a cosine. Otherwise, it would happen having alpha and gamma here. Okay. Now, therefore, beta plus 2 times alpha times cosine of 0.1 needs to be 0, and beta plus 2 alpha cosine of 0.4 should be equal to 1. Now, very simple equations, and you'll get alpha be equal to minus 6.76 and beta will be equal to 17.45. With this point of view, the statement plus beta plus 2 times alpha times cosine of omega remains positive. Okay, here you see. Okay, so the amplitude will be positive and the phase is completely linear. As a result, the desired system is y of n is equal to alpha times x of n plus beta times x of n minus 1 plus alpha times x of n minus 2, an FIR filter. Now, take home. Write a program in Python to confirm the result of filtering. The first question. Determine the attenuation of the first component. 2. What's the gain of the system in the passband for high frequencies? 3. Change the coefficients of the difference equations so that the gain of the filter be equal to 1, 0 dB. All parts need to be done inside the program.